that may or may not be the title. I told you that there are two possible titles for this talk.
That's the one.
That's good. So, what is this talk about? It's about these sorts of things. I think we might have quite a mixed audience. Who's not a scientist? There's some music people in the audience, right? That's fine. There's a range of different people here. I'll be saying things that work better for different people, but there should be something for everyone. So, here are two players. These are serious players. I'm a non-serious player. So I've been a bad guitarist for many, many, many years. And guitarists, like Taddeo on the right here, classical guitarists typically play with their fingernails. Lutenists, like Jack Herringman on the left, don't believe in fingernails and use the flesh of their fingers. Having struggled for many years to try to preserve fingernails, I saw the light about a year ago and cut off my nails, and I'm now a bad lutenist instead of a bad guitarist. Nobody lets me just music on it, but so lutenists will be playing as they play with the flesh. So I was doing that kind of thing, and something gradually dawned on me, which was that I didn't understand what I was hearing. So, when you switch from playing with nails to playing with flesh, there's a change of sounds, no controversy about that. Having cut your nails off, you then go back and you pick the guitar up and you play it again, and it sounds really, really boring. There's something really dull about the sound. But, at least in principle, now Marty's got strings. No, he's got nylon strings. So this guitar and this lute, Jacob Harrington's lute might have gut strings, but quite often the top strings on both instruments are just plain monofilament nylon, same material. They end up sounding different for various reasons, most of them uninteresting, as I'll say in a second, but you strip those away and you get left with a puzzle, which is that with a science background have either been taught or have themselves taught to many generations of beginning undergraduates the simple theory about what happens when you pluck a string. It's one of those things that's in everyone's first course on Fourier series that you do rather early in lots of courses. And those of you who do this sort of thing, you cast your mind back to what you tell your students, or what you were told if you are a student. If you can remember how that argument works, there's absolutely nothing in what that argument says that should be affected by the tension of the string or by the diameter of the string. And that's the main thing that's different. Lute strings are much more lighter gauge than guitar strings. And there's something about light gauge strings which sounds different. It's obvious when you do it. I'll show you in a second. And it's gradually dawned on me that why am I hearing this? This isn't what we tell our students every year. This is not what's in my problem sheets. So that's what we're going to talk about. So, why does a guitar sound different from a lute? Well, there are lots of reasons, and let me discard all the ones that we understand perfectly well that I'm not here to talk about. So there's a sort of guitar here, which I'll make a noise on in a second, and there's a sort of lute here. Two different sound boxes, different resonances, so that the strings are attached to different shaped bodies. Of course, they're going to sound a little different because of that. Regardless of everything else, we kind of understand that. We know how to do measurements for that. Nails versus fingertips, just the change from plucking with a hard plectrum, whether it's a fingernail or a plectrum that looks like a plectrum, or an eagle's quill, or any of those other funny things that people will use. The difference between that and using soft flesh, that we do tell our students. We're not wrong about that. So what we tell our students about plucking a string is that it's a kind of initial value problem. What you do is you get hold of the string, you pull it to one side, into some shape, and then you let go. And the way the argument goes is that you take that initial shape, more or less triangular, and you describe that as a combination of the mode shapes of the string. And the mode shapes of the string are sinusoidal. That's an uncontroversial thing. So you take that initial shape, you say, how much do I need of these different sinusoidal mode shapes to make up that shape? You then let go, those numbers tell you how much of each of those modes you excite and therefore how loud they are in the resulting sound. So we look at the initial shape and you map them onto sine waves. Where is the tension of the string in that? Where is the diameter of the string? It just doesn't come in. The nail to fingertip, that's just fine. The shape is different. I pull with a sharp plectrum and I have a rather sharp cornered triangle, and that needs lots of high frequency, short wavelengths to describe that sharp corner. I bend it round my thumb and I've got a very gentle curve, and so once the sine wave wiggles get as short as the size of my thumb, we don't need them anymore. We can already describe that gentle curve, and so the sound is less bright. There's less, you don't need so much high frequency. So that, we understand that, that's not interesting. And then finally we compare a particular lute with a particular guitar. Well, the actual choice of brand of string and all that might be different. None of that matters. So we strip all those things away, and then I claim there is still an effect. So if we eliminate those more or less, and the way to eliminate them is to take one instrument, like this one. And what we have here, this is the world's most boring guitar, because all the strings are E strings. So what I've done here, I started with the guitar with history. It's not part of this talk. It was a classical guitar, so it had 3 different gauges of plain nylon on the top. I've left those there, but tuned them all up to E. The machine heads didn't like tuning the G string up to E, but it did it all right. And then where the 4th string was, I've put a light gauge lute string on. So these are 4 different gauges of string, and if anyone wants to try it at the end, they're in a funny order, because the top 3 are the guitar strings you expected to find here, and the thinnest one is actually this bottom one. So we've got 4 different gauges of nylon, all on the same length, all attached to the same box with the same resonances, all tuned to the same note, and we'll see what that means in a moment. And we'll see this quite they sound different straight away. We don't, luckily, it doesn't matter that I'm any good at doing this to give you the difference. So we've got, I'm just going to play you the thickest and the thinnest. Something which we all know shouldn't have any influence. And no one seems to have noticed it before. I just played for a bit and I thought, I don't understand this. Why isn't this in the books? So I set out to do it. So that was the apparatus law. Do try it. Do any plucky people have a go afterwards. So, why is this a sensible thing to do? There's 4 different combinations. So that's what we've got. 3 strings plus a lute string. Here's the actual diameters, roughly a factor of 2 from the thickest to thinnest, so quite significantly different. Something important happens when you do this particular thing. Take the same material, it's all nylon, same length, same note. And if we take some further, those who don't like equations, there'll just be a couple of slides where you have a little virtual gauge, but the essential message is not really dependent on that. Now there are some standard formulae for things to do with stretched strings. I'm going to point to some of them, but I've recast them a little bit to relate to this particular problem with this guitar as we have it here, because I have fixed the length and I've fixed the tuned note of the fundamental, or my tuner in my phone has fixed it, and I want to see where the string diameter comes in. So I've rewritten things in terms of some arrows here. So we've got the strings have a certain density of nylon, we can look that up, certain length, 650 millimeters, a certain fundamental frequency, it's this E here, 329, whatever. The radius, this thing called A, we're going to keep an eye on that, that's the interesting thing. The Youngs wanted a string. Now, so what have we got formulae for here? So we've got a formula for the frequency of the string. Now, if you still think that strings produce harmonics, This is the reminder that that's not quite what they do. So the string you first learn about when you're a beginning undergraduate is the kind of string that only exists in textbooks because it's perfectly flexible. Now, any vibration relies on having some kind of restoring force and some kind of inertia. So you move something away from where it wants it to be, the restoring force makes it want to come back. The inertia means that when it gets there, it doesn't stop, it carries on, it goes out the other side. You put those two things together, you get a vibration. The frequency is always governed by the balance of those two things. The ideal textbook string, the only restoring force is coming from the tension of the string. And you pull the string sideways and the tension is no longer pulling in the right direction. There's a bit of the tension that's pulling back towards where you were. But real strings have a second effect, which is that even if a string is very slack, think of piano strings. Now, piano strings are not what you would ordinarily call a string at all. You think you're trying to tie a parcel with piano wire. Now, even when they're not under tension, they resist being moved away from where they wanted to be, and that's because of bending stiffness. The string is stiff, so even without the tension, you bend it and it wants to straighten again. And that's an independent effect. And that's all there, any real string has that. That depends on the Young's modulus, the stiffness of the material. So the actual, we get this formula, so the nth string frequency, we forget about this right-hand term for the moment, let's forget about that. This says, you start with fn squared is n squared times f1 squared. That's the harmonics you first thought of, just squared. But there's another term added to it, involving the stiffness of the string and some stuff, factors of pi, into the fourth, so the number comes in a different way. And this depends on the radius of the string, when the other one didn't. So there's a radius in there somewhere. So the actual frequencies of a string are not quite harmonic. They get progressively sharp as you go up the mode series. And thicker, fatter strings do it more than thinner, flexible strings. That's one of the differences in sound between a piano and a harpsichord. It's really thin wires and fat wires. Or between, when my guitar was tuned ordinarily, any classical guitarist knows that the E string, the top string, sounds different from the third string, which is always rather soggy sounding on a classical guitar, just because it's thicker nylon and this bending stiffness effect is bigger, and the overtones you're hearing are less accurately harmonic, and that comes out as a kind of fuzziness in the sound. So we've got something to do with the frequency. This is the frequency for the fundamental, the equation for the fundamental frequency, which I've just rearranged to say it's an equation for the tension once I've said the F1 frequency I've tuned it to in the length and the density. And you see something about that tension expression, which is that the tension is, we recognise this pi a squared as the cross-sectional area of the string. The tension is equal to the area multiplied by something, therefore that something must be the stress. So this thing is a formula for the stress. Now there's an A here, but there are no A's in this. That's the reason why it's interesting to have strings of different gauges of the same length tuned to the same frequency, is that the strings, they are very different tensions, but they're all in the same state of stress. And the stress is what the material knows about, and that's important for the behaviour of the string, because that's going to eliminate another aspect of things that could be varying if we listen to the actual strings as they were ordinarily tuned. They're all in the same state of stress. It means the physical properties of the strings are the same. And to explain that, I need to tell you a little bit about this chap called Nicholas Lynch-Aird. Some of you at least have met Nicholas. This is a scene in Nicholas's garden shed. He's someone who came to talk to me maybe 5 years ago. He's based not very far from Cambridge. He's a kind of control and instrumentation electronics engineer by background. And I think he did all right for himself with the company, so he's semi-retired and he wanted something interesting to do. And his wife plays the harp. So he got interested in the problem that the harpists have a particular problem with tuning. Because they tune the harp, then they sit for, 3/4 of an hour until their entry comes, by which time all those violinists have been breathing around them, and the first note they play is out of tune. So it would be quite nice if you could have something where your harp was not so much out of tune by the time you played it. Whether he'll ever end up building the device is by the by, but if you're going to think about that question, you need lots of data about how strings behave when the temperature varies and what have you. So he's built, this is his test rig in his garden shed. He has 2 of them now. He's built this surprisingly sophisticated test rig. So there's a string which goes along there between some bridge pins. It's got a force gauge at this end, and it's got a sort of motor and a worm gear at this end to do the winding. This bit of Lego here is a little robot that plucks the string inside his box where he's controlling the temperature and humidity. And various bits of the light bulbs and knots just to make it look nice. He turns on different combinations of those to control the temperature. This picture hasn't got the batch of water, there's a humidity control. And he's been gathering creep data on nylon strings, and each experiment takes several months, so no one else has ever tried this hard to understand the properties of nylon strings. And there's a backstory there that we don't entirely need to know about, except to show you one of his things. So here's one example of a test that he did, one of the early tests he did, where he took his string in his rig, he tuned it to some note, fairly slack tuning, let it settle for long enough for the string to stop creeping and settle down, then tuned it up a semitone and let it settle again, and then another semitone and let it settle again, and he kept doing that until the string broke. And this is just a graph of how much he had to wind his tuning motor against time in hours. You can't read this, but this goes up to 2,000 hours. This is several months of data. So you see the string takes settles to one note, then he tuned it up, and then it takes a while to settle to that note, then he tunes it up and then it settles. And by the end, the string never does settle, and in the end it just broke. So this is a string taken through the usable range from the lowest tension that worked up to just before it broke. And while he's doing that, one of the things he can measure is the Young's modulus of the string, so I'm modulating his tension a little bit. And when he does that, you get this sort of graph, and this graph doesn't come up very clearly. There are data points, which I can see and you can't see, but all you can see is the thick line. There's some very, very dim blue points your projector isn't showing it. The important thing, this is that same axis of through his test. And this is the Young's modulus, and the numbers you can't quite read say about 3 here, and about 11 or 12 there. So the Young's modulus of this nylon string has increased by nearly a factor of 4 over the range that you could use it as a musical string. Yeah? Because the molecules get more and more aligned as you stretch the string. Now you see why I want to have all my strings in the same state of stress, because I would like them all to have the same value of Young's modulus. So we're operating at some typical point, probably around about here. And I should use the Young's modulus at 10-ish in a minute. The strings, as they would ordinarily be on the guitar, would be lying at different places on this curve, and they would actually, among other variations, also have different Young's modulus, and that would muddy up the comparisons. Right, so back to my guitar then with these 4 strings. So we've got the cleanest experiment we can easily arrange. I can take the strings on there, I can pluck them and record some data. So here's the sort of thing. I can pluck the strings in various ways. I could do it with my fingers, like you just heard. I could do it with a plectrum, I could do various ways. The sharpest of all ways to pluck the string, and then this small print up here says wire pluck. If you want to do a laboratory pluck, which is the closest you can get to the textbook case that you get told about, then what you do is you rummage around to find someone who's got some really, really thin copper wire, the kind of thing you wind an electric guitar pickup out of. So you get a really thin copper wire, you feed a loop of it down the string, and you just pull it gently till it breaks. And at the moment it breaks, you get a really sharp step of force. It's always the same, because copper always breaks at the same force. You can control the position, you can control the direction. So it's a laboratory, and it's the sharpest of sharp plectrums you could possibly have. So I can do plucks, say with my finger or with a wire, get this kind of thing, some kind of decay in time history. We can look at that in various ways. I'll come back to this at the moment and show you one of these pictures that we tuned into it. So here's that time history just plotted again on its side. If I take the whole of that and then do an FFT on it, I get a frequency spectrum. And on here, there's a forest of little peaks. roughly equally spaced here. Those are the almost harmonic overtones of the string. We'll look at this in more detail in a bit. The thing in between is a sonogram or spectrogram, depending on which books you read, which is the reason these are drawn like this. This is a combination of frequency along here and time up here. So this is a time-varying spectrum with colours to say how loud it is. So what we've got is a series of vertical stripes, which are the different string modes, and the colours gradually fade from red to blue as we go up each one, as each of the string overtones dies over time. So we can suck data out of it, which we'll do in a bit. But the first thing is to say, can we measure any difference between these strings? Because just because you can hear a difference when I play them, absolutely does not mean we can easily measure it. The typical musical acoustics effect is that you have musicians or instrument makers saying, this is a really, really, really important effect, chalk and cheese. And you try really hard and you can barely see a difference between things. So is there a difference? And in this case, there is a difference. Now, I'm showing, if there are people here who know about spectral centroids, you can quiz me about exactly what I've done here, because I've taken a particular interpretation of that phrase. The spectral centroid is a measure of something you could do with a frequency spectrum that gives you an idea of how bright the sound may be. And roughly it means you plot a graph, you cut it out of cardboard, and you find the centre of gravity. I've chosen to do a long graph here to a particular interpretation of that because it works for me. And you can see I'm censoring part of it. I'm going to reveal more of this diagram later on. So what we've got here, so these are spectral centroid frequencies, and it's, broadly speaking, it correlates with brightness. Higher spectral centroid is likely to sound brighter. That's only an uncontroversial statement. It's a crude measure. There's all sorts of other things in there, but it gives a hint. So, this bunch of four things are my four strings plucked with my thumb. The exact thing that I did earlier, except I'll do them in order. So from the left hand, the thinnest one, that's that. And I'm not actually, just to get clean data, I have a little accelerometer stuck on the bridge and I'm actually measuring the body vibrations to get something clean. So the thinnest string has a spectral centroid that defined this particular way, getting on for 6 kilohertz. And the thickest one is down here at 2.5 kilohertz. So is there an effect? Yes, there is. Nice big effect. Here's the same thing, the same four strings, but with this wire pluck. Now, you look at any matching colour, and the wire pluck is always higher. And that's the thing we understand. That's what I expect. That the sharpest of sharp plucks compared with my thumb flesh always makes things go up. But as we go across the four strings, there's still a nice systematic trend, and it doesn't look like a small effect. So there is a physical effect going on here. Rather a different pattern in the two cases, and we'll come back to that. Here's a nice sort of orderly progression. Here, these two look very different from these two. We're going to come back to that in a bit. So let's see if there is an effect. So where's this coming from? So here's the puzzle. Here's the thing I sort of said before. The usual description of what governs the frequency content of a plucked-string note has absolutely no dependence on the radius, and which is that we assume it's a kind of initial value problem. You have some initial shape, and the perfect triangle is what I get with my wire pluck, and so that's, well, here are some simulations. So here are my particular copper wire, which I did the wire pluck, which breaks at about 1.5 newtons. So here is a plot of the initial shape of my four strings just before the wire broke. Now the scale is exaggerated. This is the 650 millimeters of the guitar. I've plucked at the point 30 millimeters from the bridge, and this is in millimeters. So the thinnest of the strings goes about 1 millimeter at that position before the wire breaks. The thickest is about 0.3 millimeter. And these all look rather like that triangular shape. But actually, if we put these on top of each other and zoom in on this corner, we see they're not quite the same shape, and this is another manifestation of this bending stiffness effect. Anything with bending stiffness really doesn't want to be bent into a sharp kink. The higher the bending stiffness, the less it wants to do that. So the dashed line is the textbook theory, the black one is my thinnest string, the green one is my thickest string, and that's how things should. And that's what the theory is predicting just to show that behaviour there, but still, they all look pretty triangular. So we go back to the measurements. And I've showed this before, so we're going to suck things out of this measurement. And the question we must ask ourselves first, which all the science people should be thinking to themselves first of all, the first rule of research is to ask the easy questions first. Don't plunge in with something difficult till you've looked at the easy things. So, can we explain this using linear theory, or is there something non-linear going on? That's a good question to ask first. How well do we do with linear theory? So, we're going to have a look at the frequencies and look at the damping factors. And we can fit linear theory to that. So, do we understand that? And does that have something that depends on the string radius? So, here is the result of taking the thing we had in the previous slide. We can do stuff in the computer to find all these vertical ridges, and for each one I can fit a frequency and a damping factor in some way, which the details don't really matter. And this is just to be the frequencies, first of all. Now, that formula that I had earlier for the effect of bending stiffness said that the nth frequency is not quite proportional to the first frequency. It's got this extra term to do with the bending stiffness. And a convenient way to plot that is that if you take the nth frequency and you divide it by n, then if it was perfectly harmonic, you just get a straight horizontal line. But the effect of the bending stiffness is to add a sort of parabolic shape to it. So here, and again, the colours are always the same. Black is the thinnest string through to green is the thickest one. And so this is Fn divided by n. So fundamental frequency is 329 here. And this is this sharpening effect from the bending stiffness for each of the strings. And as you might have guessed, those solid lines are the theoretical formula. And I was very pleased to see this. This is not a curve fit to each individual graph. This is the theoretical formula taking a plausible Young's modulus for nylon from those measurements I showed you earlier, the actual measured radius of the string, and just saying what did the formula say. So this is an actual prediction for how those particular four strings should behave, and that's pretty good. This is where it's absolutely crucial that the Young's modulus is the same for all four strings. If these guitar strings were tuned at their normal pitches, these shapes would all be different. It would make a big difference, factor 2 probably. So that all looks good, except that I've cheated. So I haven't shown you all the data. The actual data, as well as the stuff we've just looked at, had some extra stuff in it. And the first time I saw that some years ago, that was really baffling, but you gaze at this for long enough. So this extra stuff here must be some kind of nonlinear effect. If you gaze at it enough, you suddenly realise what it is. If you just lay a ruler along any horizontal line here, you'll find that is exactly equal to that. And this second line, this list of data points, is exactly a frequency doubled copy of the first one. So there's some kind of quadratic nonlinearity going on, producing frequencies. The linear frequencies are there, and we've fitted them well. There's something else going on which is producing frequency doubled things. What do those look like in the raw data? Well, here's a bigger picture of one of those FFT spectra. So this is string number 2. This is the normal guitar E string, the only one that's at its regular pitch. Frequencies up to 20 kilohertz here. These sharp peaks here, which are say approximately harmonic. But look inside this blue circle, when there's too many peaks, you can see extra stuff. So in this range, if you look carefully, the sequence continues, but there are pairs. There's some kind of complicated pattern of extra things. Those are the things which resolve out into that frequency doubled set when you look at it rather carefully. So that's what that nonlinear effect consists of. It's producing extra stuff in this range. We keep that in the back of our mind for the moment. Where is it coming from? Why is there a quadratic nonlinear effect? Well, that's not very controversial. Presumably, it's a rather well-known effect, which is obvious in a kind of way, which is simply that when a string is moved away from its resting length, you've made it a bit longer. If you make it a bit longer, the tension's gone up a little bit. As the string vibrates from side to side, you stretch it, You go back, you stretch it again, and then you go back. So the tension is being increased twice per cycle. So it's a mechanism that tends to produce frequency double things. And it's nice and smooth and it's uncontroversial. So probably that's what's causing this. It's an effect that's most familiar to players on steel string, metal strung instruments. It doesn't do it so much on a nylon string. If you take a steel string guitar and you play a loud note, then at the beginning, while the amplitude is big, the Young's modulus is much higher in steel, so this tension effect is much stronger, and you actually hear a little pitch glide at the beginning of the note. The mean tension is higher for a bit until the amplitude dies down a bit. You actually hear a little slightly falling pitch at the beginning of the note. It adds, you'll recognise the sound even if you've never thought of it as a falling pitch. So that's probably where this nonlinearity is coming from, and not in itself controversial. I said as well as frequencies, we can get damping factors. So here's the same 4 strings, same colour. So now, as a function of frequency, I'm plotting a loss factor measured for each of those modes. And you can see there's some kind of structure curve here. And can we explain that? Does that depend on the string's radius? So we see the bending stiffness effect was predicted to be a little bit different for different radii. What about damping? This is the bit that there will be a few equations here, but the essential bit will turn into a picture at the end. Do we understand where energy loss is happening in a vibrating string? Well, yes, we do really. There are 3 kind of mechanisms of losing energy. The first is the one you want, which is that some of the energy from the vibrating string leaks out through the bridge, makes the sound box vibrate and makes sound. That's not, that's only loss in the scientist sense of the word. That's what the box is there for, to take some of that energy out and make it into sound. Second mechanism of loss, you've got nylon, it's a polymer, it's going through cyclical strains, and the stress-strain relation will have some kind of phase lag in it, and there'll be some energy. The nylon will be warming up a little bit as a result, so there'll be some kind of viscoelastic losses in the material. And the third one is that if you wanted to hear your guitar, you play it in air, not in a vacuum. So the string is vibrating through the air, which we forget about most of the time, but it is there. So there's a bit of viscous drag of the string moving through the air. So those are the main 3 mechanisms. And we can estimate all of those. This is the bit with the equation, which you can ignore. This is just to prove we could do it. I've done very simple estimates of all 3 of those. The body loss is the most crude one of all. I'm interested in effects, I think, which are going to be at rather high frequency. So I haven't got here a fully detailed model with all the resonances of the body of exactly how each string mode couples to the body. I've taken an approximation which is familiar in engineering vibration world but may not be known to the musical people, something called statistical energy analysis. It doesn't really matter except that at high frequencies, anything that's basically made out of flat plates like this will tend to behave, that the behaviour of the body gets rather featureless at high frequencies and just turns into a kind of constant. So it behaves the same as a mechanical resistance, what's sometimes called a dashpot. And if you want to know what a dashpot is, it's probably inside this ends on the back of this door. It's a thing that stops doors slamming. Inside there's a spring, and there's probably a loose fitting piston in a cylinder that dissipates energy viscously to stop the door slamming. So that's a mechanical resistance. Any vibrating platey sort of structure at high frequencies behaves rather like that. So I've just taken that model, I've just taken some value of the impedance of the body, and we can look at measurements on guitar bodies and produce a vaguely plausible number. Works at high frequencies, it won't be accurate, particularly at the low modes. And armed with that, we can get a prediction for how the loss factor should vary with things. So this eta body, that's this loss mechanism from this first thing here. It does depend on the radius of the string, that's not surprising. Thicker strings tuned to the same frequency. What do you expect a heavier gauge string? You expect it to be louder, don't you? So the fact that the energy loss into the body is bigger with a fatter string is not implausible. It depends on the mode number. It's got some numbers that we know all these numbers, the density of nylon, the frequency, the length, and I've estimated this Z. So there's no free parameters here. We've got a a definite estimate of that. Second mechanism is to do with viscoelasticity, and that's to do with that bending term. The tension effect doesn't actually put strains into the nylon, but that bending stiffness effect is bending the nylon up and down. And so the Young's modulus becomes a complex number. We know roughly what it should be. There's 2.5% plausible value for nylon. And you can plug that into an estimate and get an estimate of the loss factor to do with this viscoelasticity. Again, it has a radius in it. Thicker strings have bigger bending stiffness, so that they can dissipate more energy in bending. This one, again, there's no free parameters in. This has an n square on the top. So the higher frequencies tend to be more highly damped by this mechanism. The other one had n on the bottom, so it's the lower frequencies that are damped more. The third mechanism is about viscosity into the air. I never used to believe this until I did this plot I'm about to show you on the next slide. I pulled this out of a well-known textbook. This is Fletcher and Rossing. It's based on a calculation which anyone who's done fluid dynamics may have seen, which is the simplest prediction of drag due to a fluid flow is just to take a cylinder and just flow past a uniform cylinder, and it's done at the end of the 19th century, a classic calculation. A string is a cylinder. It's vibrating through the air. It's the same thing as the air flowing past the string as far as this is concerned. And you can get a formula from that by pulling something out of a book. We put those together. So here's my data points again. We're on log axes here, and all of these things look, roughly speaking, straight lines in this plot. So this dashed line is the prediction for each of the 4 strings of this loss into the body. This rising line is the bending stiffness effect, big at high frequencies. This higher dashed line in all the pictures is this air damping prediction. You add those 3 together and you get, as you might have guessed, these solid lines. And I was absolutely amazed at how well this goes through the data points. This damping is never predictable at this level. This is actually, I was surprised at how well the linear theories work here. So we combine simple estimates of these 3 known mechanisms, and we get a pretty good fit to this tendency here. For the thinnest string, the body damping is surprisingly unimportant. As far as the string is concerned, the air damping effect is actually much, much stronger than the body damping. But when I said we get a good fit to the theory, that's not just that the body, this is the crudest estimate, but it's not just that the body damping doesn't match. You look at the green one, and now the 2 lines are both fairly big. Neither of them separately looks like the data points, but you add them together and you get something which is fairly credibly close to the data points. I'm not worried by the fact that the low frequency loss factors are not well predicted. That's because I know I've ignored the resonances of the body of those frequencies. But that's a pretty satisfactory linear system fit to the behaviour. And of course we've still got that nonlinear effect, these clusters of extra points that aren't lying on my line. That's the same nonlinear effect that we saw in the frequencies. And there's a reason why it appears over there. I'll engage your brain for a minute now. You take a decaying sine wave and then you square it. Squaring the frequency bit doubles it. Squaring the decay, e to the minus thing becomes e to the minus 2 thing. So the frequency is doubled and the decay rate is also doubled. The loss factor is the dimensionless ratio of those 2 things, so the loss factor stays the same. So the simple prediction is that in the loss factor we should expect to see a frequency doubling, which we've already seen, but on a horizontal line, because the loss factor should be about the same. And that's kind of credible, isn't it? There's a cluster of points here which look a bit like a copy of this bit of curve that's shifted over by a factor of 2, and this is a logarithmic scale, so a factor of 2 is that far. So that's the same nonlinear things. So what we've seen there, in those 2 things, the loss factors and the frequencies, we can see linear theory working really well. It doesn't explain all the data points, but it explains some of them. We've got a really good fit to it, and both the frequencies and the loss factors do depend on the string radius. So maybe that's what we're hearing. So the first thing to do then is to take that linear bit, ignore these non-linear things, and just resynthesize using that linear theory with these fitted things that we've just fitted to the measurements. And we know how to do that. There's a formula again. It's a combination. This sum over n is just adding up all the modes. The mode shapes really are sinusoidal. So this is the particular thing I've worked out is something that's a bit similar to my measurement. I measured the body acceleration. I use this same model of the body just as a resistance. Then I will get this prediction for the body acceleration in response to a pluck of some magnitude. Mine was 1.5 newtons. That's the thing I call P. At a particular position on the string, and we bowed string people always use this symbol beta to denote the place you put your bow down. So this beta is the fraction of the string length where I did my pluck. So if it was at the midpoint, beta would be a half. But I was 30 millimeters from the end of a 650 millimeter string, so it's about a 20th of my string. And then the omega ends, these are these frequencies that we've got a decent fit to, and these eta ends are the loss factors that we've got a decent fit to in the previous thing. So we can put all that back together. But now this is the thing which puts in equation form the thing I said earlier, that you don't see A anywhere in this. There's no explicit dependence on the radius of the string. It is inside omega n and inside eta n, a little bit, but there's no explicit, but for the textbook string, where omega n is harmonic and the etas we don't even think about, has no dependence on radius. So we resynthesize with those and we listen to it. Now, I have got the sound files here. If anyone would like to hear the various measured and resynthesized sound files, catch me at the end, because you need to, they're sufficiently similar that broadcasting them on a crummy PA system, they'll all just sound vaguely like twangs. You need to hear them in headphones. Did we remember to bring some headphones? We did, very good. So if anyone would like to hear those, and when I say these are similar, these are not similar, if you want to listen to them, just catch me at the end and we can do it. But if we resynthesize from this, I can reveal the next bit of my spectral centroid plot. So here are the two we saw before. Here are my resynthesized linear theory things. And this conveys the correct impression for what you hear. You can just about hear that they are different, but their joy is similar. So there is a small effect from these linear theory things, but it's not strong, and it doesn't sound strong, and it doesn't sound like the noise you heard at the beginning. So therefore there must be something nonlinearity, something nonlinear going on. Well, we've seen a nonlinear effect. Is that it? I don't have a really crisp answer to that yet. It's not so easy to do a neat resynthesis of the sort of thing I just showed you, which was this sort of thing here. There are extra peaks here that will be raising the spectral centroid a little, so he's probably part of the answer. But I've made some crude attempts to do this, and again, it didn't seem to make a really big difference to the sound to me. So and for reasons that I'm about to say, I'm sure this is not the only effect. I don't think it's the main effect, although it may still be there. So I think that that's not easy to resynthesize that accurately, but I think the answer is that doesn't explain it, or at least all of it. But there's something else going on. Let me look at the data again. Now, these are frequency spectra. String number 3, that's the old guitar second string tuned up to an 8, thick string. The measured frequency spectrum, and this is the resynthesized one. I've only displaced them so you can see it. There's no significance in the amplitude. Now, look at this. Here's what the theory says when you synthesize a thing like that. You get these almost harmonic peaks. They're not quite harmonic. That's all in there correctly. You've got roughly the right loss factors. And there's this modulation pattern. And that modulation pattern is associated with where you pluck. And it's from that beta effect. Now that's a completely familiar effect to all plucked instrument players. You get a difference of sound. I'm plucking in different places. This modulation is the main way that is happening. What is happening is actually easy to see. Remember, I was plucking about a 20th of the way. Well, think of plucking in the middle. If you pluck right in the middle of the string, you drive plenty of the fundamental mode of the string. The second mode of the string has a nodal point there. And so you simply can't drive that by plucking in the middle because he doesn't know you're there. Third mode, plenty. Fourth mode's got a nodal point again. So if you pluck in the midpoint, you get number 1, number 3, number 5, and you miss out number 2, number 4, and number 6. You move your plucking point to a more realistic place near the end. If you're a fifth of the way along, then every fifth one is missing. I was a 20th or 22nd or something of the way along, so every 20th one was missing, 20, 40, so on. So that's that modulation pattern that's coming from taking sinusoidal shapes, and how big is that motrip at the place I've plucked. So that's coming from a well-understood, simple mechanism. Now you look at this data here, and now you need to switch on a bit of eye of faith here, but you can see traces of that pattern. So it's biggish, it gets smaller, it grows again. Now this is the region where we've also got these extra peaks from the nonlinear thing. But then it dies away again, and there's a sort of null here, and then it gets bigger again. You know, so you can see the traces of that pattern in there. Not perfect, absolutely not. Here is the second string, the regular guitar E string, slightly clearer. Bing, bing, bing. You know, not as clean as this, and with these extra nonlinear peaks, but still doing something I can recognise as roughly what I was expecting. We do the thinnest string, and we see something very, very peculiar. This is the top string. Here's the prediction, always plucked in the same place. Here's the measurement, and it's got a kind of minimum, but it's in completely the wrong place. So this is number 14 or something rather than number 22. Now, there is nothing controversial about where I plucked, nor about the fact that the motrix on the string are still pretty much sine waves. So no plausible, sort of simple modal superposition linear theory is ever going to do that, is ever going to put this minimum at the wrong place. And nothing at all happens after that. So there's something really peculiar going on here, where it just doesn't, even with as much eye of faith as you could think of, you don't see the right behaviour. Here's another view of things. You need even more eye of faith here. Now these are these sonogram plots here. This is just the very beginning of the note, the first few cycles. This is for the thickest string, string number 4. Here's what the ideal resynthesized thing looks like, with no body resonances or anything. So remember, this is frequency along here, this is time running up here. So at time 0, I pluck it, I put in loud stuff across all frequencies. Waves travel off down the string, and after a while they come back. So that's this ridge coming back, having gone to the end of the string and back. And it's just a little bit quieter. Then it goes round again and again and again. So that's just the reflections bouncing up and down the string, getting a little bit quieter each time as it dies away. This pattern of red blobs with yellow intervals in it, that's this modulation pattern here. There is less energy here at the 22nd and the 44th and so on. The ridges are a little bit curved because of this bending stiffness effect. The high frequencies travel a little faster. That's another view of what this bending stiffness does. Okay, here's what the measurements of the same thing looks like. Now you do need quite a bit of eye of faith to say, oh yeah, they look pretty similar to me. Well, of course they don't entirely look similar, but I want to draw attention to key aspects that do look a bit similar. There's blue space up in this corner here, because we've got the loss factors about right. You go up any particular vertical line, and on the whole it's hottest at the bottom and it's getting cooler as you go up. It can be interrupted because these waves are travelling and take time to come back. But the peaks get, on the whole, quieter. You can just see a trace of these curved lines, maybe. So maybe that's just about credibly what we were expecting. Here's the same thing for that thinnest string, which did something very odd in the spectrum. Same kind of thing here, the bending stiffness is lower, so these are closer to being horizontal. Now look at this. Here's the moment of plucking. The very loudest thing in this whole plot is this blob here. That's one whole cycle, or maybe it's 1 or 2 cycles after I plucked it. Something really loud is happening. And actually, there's a central reason for that, which all plucked instrument players are familiar with. It's a buzz, schwoi. The most significant thing. So we've got heavy gauge strings that are really tight, and we've got light gauge strings at the same frequency, so they're really loose. And the natural consequence of that, you hand it to a player, they'll want to make roughly the same noise on all of them, so they will pluck the thin string to much larger amplitudes than the thick string. we've got a certain amount, there's all kinds of clutter here, there are frets and things. You pluck hard enough and you can get a fret buzz. If I do it deliberately, you could hear that buzzing. Most guitar makers spend a long time trying to get rid of things like that. But it's a candidate. It would do the kind of thing we just saw in that previous slide. I pluck it down here, the wave travels up, and by the time it comes back, it's got louder at some really high frequency. So if what that did was hit on this top fret here, so I plucked it with my thumb, perhaps with rather not much high frequency content, but it then has an impact with this bit of metal here. That puts in a rather sharp force which can excite much higher frequency stuff, but we don't hear about it down here until the waves have time to travel back down. So one period after I plucked it, something loud arrives back. That plausibly could be a signature of a buzz. Whether it's the fret or whether it's the jaws of the nut, what have you, that's another matter. I forget to say that when I roll down here, but buzzing seems credible. So we could have an impact with the fret or with the nut. Or if we've been talking about the lute, which we aren't here, but we will eventually come back to the lute, nearly all the strings on the lute are in double pairs, two of each note. They can clash together. Now, Murray's lute is a typical modern lute with the frets are tied pieces of stuff here. He's got single pieces. As I'll show in a moment, older lutes actually often have double frets, and that gives us another possible mechanism for buzzing. So maybe we're seeing something to do with buzzing, which gives us short pulse, which gives a mechanism for giving high frequencies. Now, this is not unprecedented. There are musical instruments out there which we know deliberately do that kind of thing, deliberate use of buzzing. So the sitar will show on in a minute, or if anyone knows what the bray harp is. I mean, we think of the sitar as exotic and Eastern, but European instruments back in medieval times, they seem to like buzzy noises, and there are harps which have deliberate buzzy things near the bridge to make this kind of noise. Here's our typical sitar. This is probably, with this luck, is it playing? Know what a sitar sounds like. That's the noise of a deliberately engineered buzz. Yeah. Do you know how those work? The bridge, so the sitar is the complicated version, the tempera is the simplest kind of drone instrument that does the same thing. So you've got this very wide bridge and black bits here. Here's a sort of PowerPoint sketch of a cross-section through that. Here's the string coming up, going through a little notch, and then going off over here to the playing length. Here's this wide platform bridge, and it starts out with a very, very small clearance, or it may even start out actually touching the bridge. Then you feed a bit of tuft of black stuff in behind it, and you fine-tune that till you just lift this off by just the right amount, so you control how easily it buzzes against this deliberately engineered wide bridge with a hump to buzz against here. And you can have more or less of it, and then exactly how you play, and that makes a difference. So there, deliberately, the player is fine-tuning this buzzing. Early lutes usually were not fretted, as you saw this one here with a single run. It has two pieces of gut tied around it. If you fret a string against a double piece of gut, the back one terminates the string, and the front one, what's that there for? Well, it's a buzz promoter. I think they were deliberately doing something which made it just that little bit more likely to do a bit of this buzzing. So, I gave this talk in Cambridge at the beginning of last term, and I stopped at that point. And someone in the questions at the end said, all right, put your money where your mouth is. If you think that's the reason, then you should do another experiment. You can take your guitar, and just get a bit of metal rod and feed it through on the first fret. Lift the strings up so it definitely isn't buzzing on that first fret. See if the problem goes away. And so I did the experiment, as all experimenters will recognise, that kind of worked and kind of didn't work. Here is the final bit of my spectrocentroid plot. So that's the 4 strings lifted by a rod. Now, and a wire plug. So it's a direct comparison to this lot. Is it different? Yes, it is. Less difference across the strings. Are they as similar as this? No, they're not. So there is still an effect. So lifting it up and removing that fret buzz possibility has definitely helped, but it hasn't taken things all the way down to match with this. Just exactly what the reason for that is, I'm still not. I mean, that might be this quadratic nonlinearity that we already had. I'm not sure of the answer to that yet, but it's, as a musical acoustics observation, it's really rather typical. You think, okay, I understand that perfectly now. Oh, right, well, I understand can't. There's always something else left. But, okay, that's my conclusion. My conclusion really about the lute, then, is, and this makes sense historically, it's right on the cusp of musical taste. Modern guitar makers go to, my son is a guitar maker, go to enormous lengths to avoid buzzes. People, players immediately grumble about buzzes. Flamenco players, maybe, are happy with this sort of thing. But typical classical guitarists do not want buzzes, and they will engineer it out. You go back into medieval times when people were building things like the Bray Harp, where they were deliberately putting rather gross examples of this kind of buzzing in. I think the lute is just right on the dividing line between these. It doesn't strike you, at least you listen again to the lute and you think, okay, maybe I can hear that buzzing. It relies on that brightness of tone, even when played with finger flesh, which is probably being helped by a little bit of buzzing of one thing or another, but not too much, just some, but not too much. Not so much that you mostly think of it as buzzing. The sitar is kind of obvious. It's not as gross as that, but neither is it as bland as the classical guitar. It's just on the cusp in between. Now, I don't know, the last time I gave this talk in Southampton last week, and Liz Kenny was in the audience, and this time I started saying things about players may notice this, players may notice that. She was nodding, so I'm happy to say this again now. What this suggests to me, think about the temporal player carefully adjusting to get just the right amount of buzz. These buzzing things are very, very finely tuned to little details. So this suggests that the lute might be rather more twitchy than a classical guitar in terms of small changes of weather, for example. The wood moves around a little bit and you get a bit more buzzing or a bit less, so the instrument sounds a bit harsh today or sounds a bit boring today. You have to do something different. And so I was pleased to see a player nodding when I said that. So I think that might be, you might expect the lute to have that be a bit more twitchy. And I'm sure makers are aware of that. Whether they think that this is what they're doing, controlling just a subliminal amount of buzzing, not enough to sound like a buzz, but enough to give you the brightness. I don't know. So my last slide is one that I nearly always end talks with. I think the message of this is the typical perceptual thing. You've seen this picture before? Can you see a dog? Computer people, cast your mind to the question, could you write a program to look at things like this and tell me if there was a dog there? I don't think anybody could do that still. Enormous developments in computer recognition of speech and what have you. But we're better. There are things that our brains are very good at doing. There are things that computers are better at doing. But there are things that we have learned to do. So we know things about dogs. Because once you've seen it's a dog, and because you know things about dogs, you can see things that aren't even there. You can see some legs here. You just know there's a back leg here. There's very little evidence of that. It's just that you know what it ought to be like, and so you start to see things. Our senses work like that. A musician is someone who chooses to spend a lot of their life focusing very tightly on certain subtle differences of sound. So of course they develop pattern recognition software in their heads for noticing really, really subtle things. So have we explained everything a musician worries about? No, of course we haven't. Have we made some progress in the right direction? Probably we have. Can we tell if there's a dog there? I don't know. That's all. Thank you.
Thank you very much. Jim, for just absorbing talk. We have time for, I guess, a few questions, if anybody has a
Any guitarist
question.
will try the strings do. Anyone wants to hear the sound files, we can arrange it.
Sure.
I have a question regarding the measurement. You said you put an accelerometer on the bridge
Yes.
to record the waveform. So is the accelerometer is going in the vertical direction,
Yeah.
is that correct?
Yeah.
But the plug is going in the horizontal direction somehow. And then you mix it.
No, these ones I plucked in the vertical direction. Instrument players control the plucking angle in all sorts of ways. That's not usually what the teacher talks about, but all this tirando, apoyando, thumb inside, thumb outside, a lot of that is to do with controlling the polar. There's always a bit of both polarizations there. When the string vibrates absolutely strictly parallel to the soundboard, you get very little sound. It's hard to do it. You can do it with the wire pluck. You can really carefully do it horizontal, and then you can hardly hear it at all. Anything else that you do with your finger, there's always some vertical stuff, and that implies force in the direction you want. You need the soundboard to be vibrating that way. So yes, that's what I've done, was this, and that my wire plucks were actually vertical. My thumb was whatever it was. I did what I did, but I tried to do the same on all four strings. So you're right, there's an issue there, and it could be a source of variability. But so the wire plucks, at least you always know exactly what you put in. Who knows what you're actually doing with your fingers? But yeah.
I was gonna, I don't know, like you talked about that nonlinearity problem that can double the frequencies. Mm-hmm. Isn't that perhaps as well maybe an effect of coupling between the polarization and direction? I don't know.
Yes, okay.
Suggesting.
Yeah, there are linear couplings between the polarizations because of the body response, but it's also true that nonlinear effect does also tend to produce whirling motion of a free string, other things being equal. I think actually there are stronger couplings from the linear. You have to design a very careful rig to get rid of all the unwanted things before you start to see that. Actually, Nicholas's string rig we had at the beginning, if you were looking really closely at that, he's got his bridge pins, one horizontal and one vertical, precisely to get the two polarizations as similar as possible. Because actually when a string goes over a fret or over a bridge, the direction parallel to the fret has an effective length that's just a little bit longer because it can roll slightly over the fret. So there are all sorts of things that are perturbing those polarizations. But are there subtle things I haven't taken into account? Absolutely there are. Could one conceive of simulating this axial, this tension coupling? Yes, I suppose you could. I might have them in the equations, well, the standard equations are in the back of well-known textbooks. There's an interesting question in there to look into it, but the world is full of interesting questions. One thing I do want to think about, having seen that this is important, it makes you think about bowed instruments. If you've got a fingerboard with no frets, so you're holding down against a flat board, is there something of this going on all the time when you bow something? Is there, the string changing the frequency content a little by buzzing a bit against the fingerboard? Maybe. It's intriguing. So there should be a difference between a fretted instrument like a viol and an unfretted instrument, where you could take the same viol and just play off the end of the frets and see if there's any characteristic difference. So there's no shortage of further follow-up projects.
This may be specific to electric guitars, but a lot of guitarists would swear by certain thicknesses and materials of plectrums when they're playing. They'd say that certain plectrums would sound better than others when they're playing an electric guitar. So I guess this might suggest that the material as well as the sharpness of the picker would make
yes, I dare say that's right. There's an ergonomic sense as well, because the exact timing of when you release it matters. So a bendy plectrum lets go in a different way than a rigid one, and then it depends on your wrist action and what you want to do. So, yeah, I dare say there is a difference, but I dare say there's also a difference with what the player ends up doing with the plectrum. But it's perfectly, I think it's a familiar, they certainly feel different. But any of the mandolin, whatever, anything you play with a plectrum, how short you hold it and what you buy. With the oud players who have probably long lengths of turkey quill or something, the different cultures choose all kinds of different things for doing this. sitar players put metal things on their fingers, don't they, to pluck with. There are many. But yes, they're not wrong that it makes a difference of sound and feel. Musicians are never exactly wrong, it's just they describe things in language which is hard for physicists to understand. They're always worth listening to, but gently trying to focus them in about, do you mean this or that? Suppose I did this experiment with you. Oh, yeah, but that's not interesting, I don't do that. The characteristic effect of doing listening tests is you make musicians listen to things and say, which one do you prefer? And they say, I don't like any of them, they all sound horrible. Characteristic